All right. Continuing our review for the final exam. The first thing you're going to do today is go into Schoology and go in and access this one, the question type example quiz. It's basically going to walk you through about 13 questions and show you the different types of things you might see. Okay? Now, the content isn't what I want you to focus on. For example, there's some geometry questions in there. Okay? This is a test, a little quiz sampler that was created for all of our math classes. So I'm not telling you that the content in this is what's going to be on your final. What I'm telling you is these are the types of questions you might see. In other words, drag and drop, multiple choice, things where you need to do a matching or that type of thing. Okay, I just want you to get the hang of how your Chromebook is going to work. Okay, so I'm going to pause the recording. I want you to try those 13 questions. All right, so on the test question sampler, what were some of the types of things you saw? Drag and drop. Drawing a line, right? Using the drawing tool, drawing a line or a parabola. Okay, so maybe clicking on a region of a graph that you want as your solution. Matching, right? Traditional multiple choice, true, false, that kind of thing. Okay, fill in the blank. When you were having to type something in, did a keyboard pop up that allowed you to do powers and things like that? Okay, so questions on any of that in terms of the process in selecting your answer. When you take your final, it's going to be in 3 parts because we have the district has split their part into 2 and we have our school part as well. So there's 3 parts. It's a total of 50 questions. You will get 1 packet, a paper copy of all 3 parts put together, okay? And for example, after you hit question 10, it's going to say, now go in and submit these on part A, okay? Then you'll do 10 more. Now go in and submit those 10 answers for part B. The one thing I do want to caution you of, we have a printed copy. When you take your test on the computer, the answers get scrambled. So you can't go down and say, okay, I chose the second answer, I'm going to click on B. It may not match. Okay, so you are going to have to look at your answer and look through all the choices and make sure you're picking the correct one. Does that make sense? So the paper ABCD might be in a different order on the computer. The questions are in order, yes. Okay. All right, let's go ahead and correct your yellow packet. This was the first review packet. First page. Your answers are D as in dog, C as in cat, B as in boy, A as in alphabet. All right. Next page. Number 5 is C. 6 is D. Seven is A. 8 is D. 9 is D. 10 is A. 11 is D. 12 is A. 13 C. 14 D. 15 and 16 are both B. 17 and 18 are both A. 19 is B. And 20 is A. Take a look quick at the choices for your answers on 19 and 20. The notation in your yellow packet is the old notation, what you probably would have done back in 6th grade when you did division. Okay? We don't use that R notation anymore. Okay? So remember, if we were answering question 19, our answer was negative 4x squared minus 20x minus 81, and we had a remainder of negative 321. So we would say plus negative 321 over, what were we dividing by, x minus 4? Okay, that's the notation that you will see on your test. So I just want to clarify that. Okay. All right, so you are turning in the green packet. Go ahead and keep this yellow one to review. And then I need you guys to find the white packet that we started yesterday. We're going to continue that today. All right, so continuing where we left off yesterday, our next learning target was that you can perform reflections on linear functions. So we have two different types. We can reflect over the x-axis, and we can reflect over the y-axis. So let's say we have a point here, and we want to reflect it over the x-axis. Okay? If I say this is at the point xy, what happens when I flip it over the x-axis and put it down here? Which coordinate changes? In other words, if I were looking at plotting a point, say this is the point 2, 3, this becomes what? 2, negative 3, yes? So your y value changes, okay? So if we are going to make a reflection over the x-axis, we have to make sure our y changes, okay? Two ways to do that. We can say we want y to be its opposite, all right? Well, if I put a negative sign in there in front of y, I could divide that negative to the other side. Is dividing by a negative do anything different than multiplying by a negative? No. So what we really are saying is that y is going to be the opposite of what we had there. Okay? So my new expression or my new equation would be y equals negative 2x, minus 7 if we distribute. X is not, I'm saying that my y coordinate has to change sign, right? And if I have defined y to be 2x minus 7, and I want y to change, then I have to change 2x minus 7. It changes the whole expression, what y is equal to. Okay? So, in my first drawing up here, we were just reflecting one point. Here we're reflecting a line, right? We're taking a line, we want it to go the opposite direction. Okay? All right, so continuing that same column. If I have the line y equals negative 3x plus 5, and I want to reflect it over the x-axis, it's going to take everything and make it the opposite. Yes? My y has to change. My y has to become the opposite of what it was. So I'm going to change everything on the right side here. This is going to become a positive 3x, and it's going to become a negative 5. Okay? So reflecting over the x-axis makes your y value change. So whatever expression you have for y, you have to change it all. If I want to reflect over the y-axis, now I'm going to take this same point, but I'm going to reflect it over here. Yes? Now which coordinate changes? I just want to change my x value. Okay? So only x goes to its negative, which means my y stays the same that it was. And the only thing that changes is instead of my x being x, it's going to be its opposite. Okay? So only the part where there is an x is going to change signs. The 7 is still going to stay a positive 7. Okay? Let's try another one. So for this one, y equals negative 3x plus 5. All I am going to do is change that x to be its opposite. So I'm going to end up with y equals what? So a positive 3x. Okay, so my x term changes. Questions about that? So when you get to this question on your final and you're thinking, okay, I can't remember which one changes which way, all right, go back to what I did in my first drawing. Plot a point and think about it. If I flip that over the x-axis, which of my coordinates is changing? Okay? All right, let's move on. Our next learning target. I can describe the transformations of polynomials. It says write the equation for the parent function, y equals x cubed, that has a vertical stretch of 2, a horizontal shift left of 2, and a vertical shift moving down 5. Okay, so we are going to start with our parent function, y equals something cubed. Yes? That's our parent function. Now we're going to do some things to it. If we want to have a vertical stretch of 2, where would I put that 2? Goes in the front. All right, so I'm going to put a 2 here to be a vertical stretch. What kind of number would be a vertical compression? Well, be careful of saying fractions. It has to be a fraction less than 1, right? Like a 1/2, 2/3, things like that. You can't just say it has to be a fraction because I could put 5/2 in the front, and that's a stretch, okay? Let's see, we're shifting horizontally 2 to the left. My left and right moves, where do I put my numbers? In the parentheses, all right? Inside with x, right? X is my movement, left or right, x-axis. If I want to go left 2, am I adding or subtracting that 2? I'm adding 2. Good. And then my last piece, it says we want to shift it down 5. Where does that show up? Outside, down 5. Yes? So you could have a question like this where I give you the parent function. I want you to do all the transformations and create your new function. You could have be given the function and just say, okay, what kind of transformations happened? Okay? All right. So the second one here is more like that. If we start with a parent function of x squared, can you describe what we've done to it? Is there a number in front of the parentheses? So there's no vertical stretch, vertical compression. It hasn't been flipped over the x-axis. Okay, nothing like that. What is the 4 going to do? Move it which way? Right 4? Agree, disagree? Okay, and then the plus 7 at the end? 7 units up. Okay. We've talked about different types of functions like parabolas, absolute value graphs, and looking at that idea of transformations. Okay. Our A term, we said, was our vertical stretch or compression, and if it's negative, it's going to cause it to flip upside down, reflecting over the x-axis. Okay. Our H value is that horizontal shift, and our K value is that vertical shift. What shape do we have for absolute value graphs? U is a parabola. V. All right, absolute value graphs look like a V. So if you know where that vertex is, that's key, right? We need to know where that point is. And then what do we know about the slopes of the two sides? If one has a slope of 2, this one's going to have a slope of -2, right? They're just opposites. Okay, so looking at our first example, we have a 2 in front. What is that going to do? That's a stretch. So instead of my slopes being 1 and -1, now they're going to be 2 and -2. So this term is going to be the slope on the right side. Okay, so the slope on the right side is going to be a 2. The slope on the left side is going to be a -2. Okay, have we shifted it left or right at all? No. Have we moved it up or down at all? Okay, so we've gone up 1. Our normal absolute value graph starts out with its vertex at the origin. Okay, so normally we are here, and we have a slope of 1. Let's try to reorient my board here in a sec. All right, slope of 1. We now have to stretch that, and we also have to shift it up 1. Okay, so my new vertex is going to be here at 0, 1. And I want to do a slope of 2 on the right side. So I'm going to go up 2 and over 1. Up 2 and over 1. Okay, how do I get the other side? Go the opposite direction, up and then back. So up 2 and back 1. Up 2 more, back 1. Okay? So you have to know where that vertex is so you know where to change the direction of your V. Okay? All right. While I reorient my board, I want you guys to try the next question. All right, let's look at what we've done to it. What is this negative in front going to do? It's going to reflect it over the x-axis. So instead of it looking like a V, a normal V, right, it's going to be upside down. So we know our picture should look like this. Yes? All right. It also means that the slope on the right side is going to be a negative 1. All right, which is why it's going downward. Okay? And then, which way did we shift the vertex? We went left 1 and down 3. All right, so let's put our vertex in there. All right, left 1 and down 3. And we said we want the right side to have a negative 1 slope. So down 1, right 1. Okay, that gets me this side. And then I have to go down and back to get the other side. All right, shifting to inequalities. The only difference now is that we're going to have some shading, and we might have some to worry about the dotted and solid line. Okay, quick summary. Solid lines when you have equal signs, dotted lines when you don't. Okay, now the part here where that says shade above and shade below, that only works if your inequality is solved for y. Okay, so it has to be y is less than something, or y is greater than or equal to something. Okay, you have to have y by itself in order to decide that. All right, first example here. Where have we moved our vertex to? Which way did we move? Left 2 and down 3? All right, so left 2 and down 3, our vertex is here. What's the slope? 1, right? I haven't done any kind of stretching. All right, so a slope of 1. Is this going to be a solid line or a dotted line? Solid. Okay. And then I have to decide, am I shading above or below? Do I have y all by itself? Yes. So I want my y values to be bigger than what I've drawn. Okay. Which means I have to go above my v. That means I'm going to be shading everything in here. Okay. All right, continuing to look at graphing inequalities, but these are just linear ones. Okay. Same rules apply. So if we are going to graph this, I want it solved for y if I'm going to use that concept of shading above and below. Okay. So how would we solve this for y? All right, guys, I need you answering. Subtract 2x, and then what? All right, so dividing this by 3, we get negative 3. So it's in our slope-intercept form, which means we're going to start here at negative 3. That's my y-intercept. So I'm going to put a dot here at negative 3 on the y-axis. And then this is my slope. So I'm going to go down 2 and right 3. Down 2, right 3. I could also go up 2 and left 3. Up 2, left 3. Okay. Solid or dotted line? This one is going to be dotted. Okay. And then I have to decide, am I shading above that dotted line or below it? Since my inequality symbol is less than, I want my y values to be smaller. It means underneath. Okay, so you would shade down here. All right. For the next question, instead of a single line, we have a system. We have two linear inequalities, and we want to graph the system, which means we need to graph each inequality and then look for where the shaded parts overlap. Okay? Both of these are solved for y already, which is helpful. The first one, we have a y-intercept of 1, so I'm going to start here at 1, and I'm going to graph a slope of 2, up 2 over 1, or down 2 and back 1. Okay? Solid or dotted line? This one's dotted. Okay? And am I shading above or below? Above. Okay. All right. Second one has a y-intercept of -2 and a slope of -3/4. So you're going down 3 and right 4. Or up 3 and back 4. Solid or dotted? This one is solid. Shading above or below? This one is below. Okay. Now, if this were a test question, you guys just did that test sampler, you had similar things, right? Where you looked at already a pre-drawn graph. Make sure you've picked the correct graph, and then you have to pick the region where the shading overlaps. So in this case, I would have selected this part here. All right, I need to be under red but above blue, so I'm in this region over here. Okay. Are points on the dotted line solutions to the system? No. Are points on the solid line solutions? Yes. So a point on this red line over here, right? That would be a solution, but I would not use the dotted blue line. Okay. All right, our next learning target. I can solve word problems involving a system of equations using substitution. Okay, it says a ski rental agency has an initial fee of $30 and then charges $25 per hour. A different rental agency has an initial fee of $50 but only charges $15 per hour. After how many hours will you spend the same amount of money? It does say to round your answer to the nearest hour. Okay, so we need to look at the cost of each option. So the first rental agency, what is my cost? What's my initial fee? $30. Okay, and then I'm going to add to it what? 25 for every hour? Okay, so X is hours. For the second rental agency, my initial cost was $50, but I'm only spending $15 extra each hour? Okay, and the question then says, when are they the same? So really I'm saying, when does the first cost equal the second cost? So I can do a substitution. I can say this has to be substituted in to balance this side. Okay, so 30 plus 25x has to be equivalent to 50 plus 15x. All right, and then you just have a linear equation to solve. So getting x's to one side, we get 10x. Getting constants to the one side, we get 20. X has to be 2 hours. Okay. All right. This time we are solving a system using elimination. Some books call it linear combination. Some books call it addition multiplication method. Our process. We want to find one of the variables that would be easy to get to disappear. Okay, we have two equations with two variables. We need to get one of them to disappear. All right, so looking at our first example. Which variable, x or y, seems easiest to get rid of? All right, we can get rid of y simply by adding the two equations together, right? No multiplication is required. So if I simply add these together, I end up with 5x's, no y's, and it balances on this side with 5. So that means x has to be a 1. And then how do we find what y is? So can we substitute it into either equation?
Yes, ma'am.
All right, which one do you want to use?
Let's do the first one. Seems a little bit simpler.
All right, plugging this into our first one. 2 times 1 would be 2. So we have 2 plus y equals 7, which means y has to be 5. So my solution, remember, is an ordered pair. The ordered pair 1, 5. Right? X first, y second. Yep, we are. All right. Second one. Do we have variables that are opposites? Can we get opposites? All right. Which one do you want to get rid of? The x's or the y's? All right. Our process would be to pick a variable, right? Let's say we pick x's to get rid of. We have 15 x's here. We need to make this turn into a negative 15. So we would times the top one by negative 5. All right. So our new top equation becomes negative 15x minus 10y equals negative 35. Our second equation we did not have to change at all. When we add it up, in this case the x's disappeared, which was our goal, but the y's also disappeared. Okay? If they hadn't, we would have been able to solve for y, plug it back in, and get our x. But these disappeared, so our important part now is to look at what's left on the other side. Over here we end up with a negative 5. Well, does 0 equal negative 5? No. So if you get a false statement, we say no solution. What if everything had canceled? In other words, we ended up with 0 equaling 0. Then we say there's infinitely many solutions. Okay? All right, our last learning target from this chapter. I can use linear programming to solve a set of constraints with an objective function. So we have a list of constraints here. Okay, and we have an objective function. Our first step is we have to graph all of our constraints and look for what region has all of the shaded parts. Okay, we call that the feasible region. All right, so how do we graph x is greater than or equal to 1? So x being 1 is a vertical line, solid or dotted? Solid. Okay, so for this one, we're going to have a solid line at 1. And which way do we shade it? If we want x to be greater than 1. We're going to shade to the right. Okay, I'm just going to draw an arrow there. I do want you guys to lightly shade yours. It's just I can't lightly shade up here. Okay? It would be. All right. Second one. How do we graph y is greater than or equal to 2?
Solid line at 2.
But this time it's horizontal?
Yes.
Okay. And shading up or down? Above or below that? Up. We want y to be greater than 2. Okay, so you should be shading above that. Okay. Next one. Y has to be less than or equal to 5. So now we have a horizontal line at 5, but now we're shading below. Okay, so we have basically said we're limiting our answer to in between that red and green line, right, and to the right of the blue line. All right, last question, or last constraint. X plus y has to be less than or equal to 7. We can solve that for y simply by subtracting x to the other side. Okay, so now we have it in slope-intercept form. We're going to start at 7, and we're going to do a -1 slope. All right, solid or dotted? Solid again. And are we shading above or below it? Below. So if I have to be above red, below green, to the right of blue, and underneath purple, my feasible region
Trapezoid.
would be in here?
Wait, no, it's not trapezoid. Is it?
Yes, that is a trapezoid.
Oh, bam! Let's go, boys. Right angle.
Okay,
And right angle.
moving on. Our next step. We found the region where they all overlap. Now we have to find the vertices. Okay? All right, so I want you to list the vertices. We're going to make a little table. All right, so this first point right here, what are the coordinates of this one? 1, 2? All right. Doesn't matter the order you go in. I'm just going to keep going around. That one has the coordinates 1, 5? Yes? Okay. This point? 2, 5. And last one here. Okay. So for each vertex now, we have to plug them into this objective function and see what value we get. Okay? So P equals 2 times my x coordinate, which was a 1, plus 3 times my y coordinate, which was a 2. What do we end up with? 8? Okay. Next point. We have 2 times 1 plus 3 times 5. Okay. Next vertex. We have 2 times 2 plus 3 times 5. And our last one, we have 2 times 5 and 3 times 2. So the question was, find the maximum value, right? Which one gets us the biggest amount? So I would say my maximum is 19, and it happens at the point, what was it, 2, 5? Okay. All right, questions?
This is really like deja vu.
It should be deja vu because this is review of stuff we've done this semester, right? Okay, so next packet, which one do we number? Number 3 is the purple one? Yes? So you're doing purple one for tomorrow. Green ones you're leaving with me now.